Today we are going to discuss about experiment A, which is verification of Bernoulli equation. 1.1 is the objective of the experiment to demonstrate Bernoulli equation by observing the relationship between pressure head and kinetic head. It validated the equation by applying it to the steady flow of water through a taper conduit. Practical observational data collected confirm the accuracy of Bernoulli principle in describing fluid behavior. And so let's move on to 1.2, which is the background experiment. The Bernoulli equation is a key principle in fluid dynamics that describes how a fluid moves along a streamline. It is based on the law of conservation of energy and is expressed by this equation, which is P is a fluid pressure, ρ is a fluid density, V is a flow velocity, Z is the height, G is the acceleration due to the gravity. This equation means that the total energy, which is pressure energy, kinetic energy, and potential energy per unit volume fluid, remain constant along a streamline in steady and incompressible flow. The Bernoulli equation is widely used in many fields like aerodynamics, hydrodynamics, and engineering. In hydraulic engineering, it is used to design efficient water supply to ensure steady flow and pressure. Bernoulli's principles state that when speed of fluid increase, then the pressure decrease. In this experiment, measure fluid pressure, speed, and height in different points along a streamline. Early experiment used water column and manometer to show pressure changes in flowing water, proving the equation accuracy. The description of specialized equipment 1.3. In this experiment, a flow bench with clear fluid conduit, pressure gauge, a manometer, and a speed meter. This tool help measure fluid pressure, speed, and height at different points. The importance of this experiment is by checking the Bernoulli equation is crucial for engineering and understanding how fluids work. By confirming this principle, we can design and improve systems that use fluid flow such as pipelines, pump, and ventilation system.
We move to methodology. Let's begin with the equipment used. We use a Bernoulli apparatus connected to a hydraulic bench, which allows us to maintain a steady water flow and measure the flow rate. A manometer was used to record pressure at 11 different tapping points along the tube. We also use a stopwatch for timing and a ruler to measure the distance between tapping points, which is important for plotting pressure and velocity change across the length of the tube. These instruments help us observe how pressure and velocity change through the flow path. Moving on to the procedure, we first turn on the hydraulic bench pump and gradually open the valves to allow water to flow through the apparatus. Once the system was filled and stable, we use a hand pump to balance the manometer reading at approximately 200 mm. We then open the apparatus valve until the rotometer indicates a flow of 0.007 cubic meter and measure the pressure reading at each tapping point. The ruler was used here to record the distance between each tapping point along the conduit, which allows us to plot pressure head and velocity head against distance accurately. This entire process was repeated to three different diffusional heads that 200 mm, 250 m, and 300 mm, giving a range of data sets to analyze. These readings were crucial in calculating the static head and velocity head at different sections of the tube, which helped us understand how energy transforms throughout the system. To move to result from the experiment, we obtained three sets of data, each with a different diffusional head. Table 1 shows result for 200 mm, Table 2 for 250 m, and Table 3 for 300 mm diffusional head. The first graph shows the relationship between static head and distance. As we can see, the static head gradually decreases with the distance, especially through the narrower section of the tube. These trends reflect Bernoulli principle, which states that as the velocity of the fluid increases, the pressure must decrease. The second graph displays total head versus distance. Ideally, this value should remain constant, and our graph support this. The length is nearly flat, showing that energy was conserved throughout the flow. Any small variations are likely due to minor loss, like friction or turbulence in the apparatus. The third graph represents static head versus tapping number. We notice a sharp pressure drop around tapping number 6, which is the narrowest part of the tube. This is where the fluid reaches its highest velocity, leading to the lowest pressure, again confirming the inverse relationship predicted by Bernoulli equation. Finally, the fourth graph shows total head versus tapping number. Despite some small fluctuations, The total head remains relatively stable across all tapping points. The stability demonstrates that even as pressure drops, the increase in velocity balance the energy, thus confirming conservation of energy in the system. We move to methodology. Let's begin with the equipment used. We use a Bernoulli apparatus connected to a hydraulic bench, which allow us to maintain a steady water flow and measure the flow rate. A manometer was used to record pressure at 11 different tapping points along the tube. We also use a stopwatch for timing and
Okay, now I'll talk about the discussion part of the experiment. From the table as we can see, when the tapping number is increased, the static head will go down. At the same time, the fluid speed is increased. This shows how energy is being converted from the pressure to the velocity. So basically, when the fluid is moving from a larger area to a smaller area, the pressure drop will happen. At the same time, the velocity will increase. This is because the energy is changing form, but the total energy is still the same. Next, we can see the total head, which is pressure head and velocity head, are stay almost constant with the distance. That is a good sign because it means energy is being converted properly and efficiently, without much loss. Lastly, we can notice that when the flow area is getting smaller, the fluid velocity is increased. This is because the flow rate needs to stay at the same, so in the small area, the fluid has to move faster. Now, let's look at the sum error and how we can improve the experiment. First is the air bubble inside the tube can affect the pressure reading. So before starting the experiment, we should remove all the air bubble to make sure the reading is accurate. Second, when we read the pressure scale, our eyes is important. If our eyes are not same level with the pressure reading, it will cause parallax error. To avoid that, we should always make sure our eyes at the correct height when taking reading. Sometimes the water flow is not steady. If the flow keeps changing, it affects the pressure and velocity. To fix this, we should control the inlet condition properly to make sure the flow is in the smooth and steady constant during the experiment. By handling this small issue, we can get more accurate and reliable result. In conclusion, this experiment helped us to understand how Bernoulli equation is worked in real life. We found that when the velocity is increased, the pressure is decreased, which is matched with the Bernoulli equation predict. Even though we have some error in our experiment like friction in the pipe, air bubble, change in water flow, but the overall result is still follow the pattern. In conclusion, this experiment not only confirm the theory but also show how velocity and pressure are related in real fluid motion, which is very important in oil and gas industry, especially for designing pipeline and fluid flow efficiency.